So in this example, we see that the integrand has an imaginary period, an imaginary period of 2 pi I. X cosh of x plus 2 pi I is cosh of x. But if we were to do if we were to change x to x plus I pi, then we would get cosh of x plus I pi is minus cosh of x. So we get a minus cosh of x. So we can't use a contour of height pi. If we were to try to evaluate this using this, then we'd find that the integral's going. So I mean, we're considering a rectangular contour, of course. If we were to use a contour of height 2 pi, and try evaluating this integral using this integrand, then what would happen is that the integral along here would exactly cancel this integral along here, and we'll get the answer. We'll get nothing. You won't get the integral you want. So this is where the technique comes in, that we consider IN, and what we need to evaluate instead is we put an z here. So if we do that, then as we take the limit as r goes to infinity, along here integrating, we'll end up with I1. Then we need to integrate upwards, so we should do this properly. So we're integrating y from 0 to 2 pi, and z in that case is equal to r plus iy, and dz is I dy, and we've got a plus cosh of r plus iy. So exponential beats polynomial. So this is of order e to the minus r, which goes to 0. That's the integral up here. Then the integral back is going to be from infinity to minus infinity of, now z along here is x plus I 2 pi, and on the bottom, because this function is periodic with period 2 pi I, we just get the same as before. So, and then this last one down here is very similar. We've got limit as r goes to infinity from 2 pi to 0. This time it's minus r plus iy, dy, and a plus cosh of minus r plus iy. And again, this is order e to the minus r, which goes to 0. So swapping the limits to get a minus sign, we end up with minus. So we get this first thing here is just exactly I1. And the second thing is what we want. So we get minus I2 pi times the integral you want, I0. So I forgot to say we're taking a to be less than 1 in this case. So the tricky thing with this problem, as always, is actually to get expressions for the poles. So but before we do that, we may as well just say, well, okay, we've got now that minus 2 pi I naught is equal to this. So therefore, I naught is equal to minus the sum of the residues of z over a plus cosh z inside the contour. So where does this have poles? Well, it's going to have simple poles when cosh of z is equal to minus a. Now what we can't do is just write, oh, therefore that's where z is equal to inverse cosh of minus a, because that's not a real number. So we have to do a bit of work and work out exactly where on the complex plane this happens. So remember our technique for doing this. We write this out using a formula. So cosh of z is cosh of x cos y plus I sine x sine y. And that's equal to minus a. So a is real, and that means that this thing here has to be 0. Now what we know is the solution to this, z equals x plus iy, cannot be real. Therefore y cannot be 0. So that means x must be 0. So we know that x is 0, and that means that y has to be a multiple of pi now, okay, we're only interested in poles we're only interested in poles in this region here. So in fact, we're going to end up with just n equals plus 1. Anyway, so we've got y sorted out. Forgot to write x equals 0. Sorry, I'm talking rubbish. Sorry, x is got to be 0. So yeah, we're free to choose y. So if x is 0, then we've got cos y is equal to minus a. So therefore, y is equal to inverse cos of minus a. And inverse cos of minus a, if we draw a picture of what cos looks like. If this is a and this is minus a, we're trying to keep this, this is pi, then there should be two solutions, but because of the symmetry, those two solutions are going to be pi plus or minus inverse cos of A. Okay, this distance here is going to be the same as this distance here. Okay. So finally, we're going to end up, y is the imaginary part of the solution to this. So that means we're going to end up with poles at, this is pi, we'll end up with poles here and here. So the poles are at I times pi plus or minus inverse cos of A. So we need to work out the residue at those poles. So the residue of that function at, so I'll just call it z plus or minus. Is going to be, so we'll do the p over q dashed. So this is p, this is q. So I'll have I pi plus or minus cos to minus a on the top, and I need sine of, when I differentiate cos I get sine of I pi plus or minus cos to minus a on the bottom. So sine of iz is equal to I sine z. So that's going to give me, the I is going to cancel with this I, and I get pi plus or minus cos to minus a over sine of pi plus or minus cos to minus a. So I need to know the plus pi will give me a minus sign when I've got x, sine of x plus pi is the same as minus sine of x. So I can get rid of the pi and get a minus sign. Then so let's do that. So I'll get rid of the pi and get a minus sign. I can also, that will leave me with sine of plus or minus inverse cos of A. Now that plus or minus, I can take out the front, and multiplying a plus or minus by a minus overall gives me a minus or plus. So I get minus or plus, and that just leaves me with sine of inverse cos of A. So I need to work out what this sine of inverse cos of A is. That's easy to do with a little triangle. Right angle triangle with an A here. So inverse cos of A is this angle here, and sine of that angle is this distance here, which by Pythagoras is 1 minus a squared. So this quantity here is root of 1 minus a squared, and multiplying the top by minus or plus gives me minus or plus pi, and then minus or plus times plus or minus, it gives a minus overall in both cases. So we get minus inverse cos A. Right, so I need to sum these residues, and there's a minus sign. So when I sum the residues, the minus or plus part will cancel out, and I'll just end up with two of these, and I've got a minus sign here. So overall final answer is I naught is 2 times inverse cos of A over 1 minus the square root of 1 minus A squared.